In the vast cathedral of space, where light bends and time stretches like molten glass, lies a possibility so profound it reshapes the very ground beneath our understanding of existence. What if everything that has ever been, every star that has ever ignited in the cosmic dark, every galaxy that has ever spiraled through the void, every moment of consciousness that has ever flickered into being, exists not in the universe we think we inhabit, but on the surface of something far more mysterious? What if reality itself is nothing more than information encoded on a distant boundary, projected inward like shadows dancing on the wall of an infinite cave? What if the depth we perceive, the volume of space between atoms, the vast distances between worlds, all of it may be an elaborate illusion, a holographic projection from a two-dimensional surface so remote it lies beyond the reach of light itself? For decades, physicists have gazed into the heart of black holes, those cosmic graveyards where matter vanishes beyond an event horizon, never to return. They are regions where the familiar laws of physics break down completely, where time slows to a crawl and eventually stops, where space itself becomes meaningless. These are the universe's darkest secrets, places where reality goes to die. Yet buried within the elegant mathematics that describe these cosmic monsters lies a revelation that turns our entire conception of existence inside out. The equations whisper of something impossible, a universe that might not exist in 3 dimensions at all, but rather as information written on a 2-dimensional surface, a hologram of unimaginable complexity and beauty. If this is true, then we are not merely observers of cosmic mysteries scattered across an vast empty stage. We are living inside the greatest mystery of all, prisoners of an illusion so perfect we mistake it for reality itself, inhabitants of a cosmic black hole whose event horizon encompasses everything we have ever known or ever could know. The story begins in the winter of 1975, in a modest office at Cambridge University, where the boundaries of human understanding were about to be redrawn forever. Stephen Hawking, a young theoretical physicist whose brilliant mind had already begun its battle against the motor neuron disease that would confine him to a wheelchair, sat surrounded by equations that would soon shake the very foundations of physics. The chalk-covered blackboards bore witness to months of painstaking calculations, each symbol a step deeper into the mysterious heart of reality itself. Outside his window, the ancient spires of Cambridge reach toward a gray English sky, their stones having witnessed centuries of human inquiry into the nature of existence. But inside that small room, Hawking was probing questions that stretched back to the very birth of the universe, wrestling with mathematical demons that had confounded the greatest minds of his generation. For months, Hawking had been pursuing one of the most profound questions in science. What happens when the strange, probabilistic rules of quantum mechanics, the bizarre laws that govern the smallest particles in existence, collide with Einstein's general relativity, the elegant theory that describes gravity as the curvature of space-time itself? These 2 pillars of modern physics had never been successfully unified, standing like isolated towers of knowledge that seemed to describe completely different universes. Nowhere was this tension more apparent than at the edge of a black hole, those cosmic monsters that represented the ultimate testing ground for the laws of physics. Black holes were regions of space-time so dense that their gravitational pull warped the very fabric of reality into an inescapable prison. Nothing, not matter, not light, not even information itself, could ever escape once it crossed the event horizon, that invisible boundary beyond which the laws of cause and effect seemed to break down completely. Einstein himself had been deeply uncomfortable with the existence of black holes, hoping they might prove to be mere mathematical curiosities rather than physical realities lurking in the cosmic dark. The equations of general relativity predicted their existence with mathematical certainty, but their implications were so extreme that they seemed to violate common sense itself. How could regions of space exist where time itself came to a stop, where the familiar notions of past and future became meaningless? Yet observations were beginning to confirm their reality. X-ray telescopes detected the violent death throes of matter spiraling into these cosmic whirlpools, and radio astronomers mapped the gravitational distortions they created in nearby spacetime. Black holes were not merely theoretical constructs. They were real, and they were everywhere, scattered throughout the galaxy, like cosmic graveyards marking the death of massive stars. But Hawking's calculations revealed something that defied everything physicists thought they knew about these ultimate prisons. As he worked through the complex mathematics of quantum field theory in curved spacetime, applying the strange rules of quantum mechanics to the extreme environment near a black hole's event horizon, the equations began to whisper an impossible truth. Black holes were not perfectly black at all. The revelation emerged from the quantum foam that seethes at the very foundations of reality, a realm where the smooth geometry of Einstein's spacetime gives way to a chaotic dance of virtual particles popping in and out of existence. At ordinary distances, this quantum foam is invisible, its effects averaged out by the sheer number of virtual particles created and destroyed in every microscopic volume of space. But near a black hole's event horizon, where the gravitational field becomes so intense that it distorts the very structure of spacetime, the quantum foam reveals its hidden power. Virtual particle pairs, normally destined to annihilate each other in an infinitesimal fraction of a second, suddenly find their fates separated by the immense curvature of space. The mechanism was both subtle and profound. As these ghostly particle pairs burst into existence from the vacuum itself, the intense gravitational field near the event horizon could capture one member of each pair, dragging it past the point of no return into the black hole's interior. The other particle, freed from its mutual destruction, would escape into space as real radiation, carrying with it a tiny portion of the black hole's mass energy. Hawking's equations showed that this process was not merely possible, but inevitable. Every black hole in the universe was slowly radiating energy into space, glowing like cosmic embers in the dark. The radiation was incredibly faint. For a black hole with the mass of our sun, the temperature would be just 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background that permeates all of space. Yet given enough time, vast eons that dwarfed not only human history, but the entire current age of the universe, even the largest black holes would eventually evaporate completely. As they lost mass through radiation, they would actually grow hotter, their final moments marked by an explosive release of energy as they shed their last fragments of matter in a brilliant flash that would outshine entire galaxies. This Hawking radiation, as it came to be known, transformed humanity's understanding of black holes from eternal prisons into temporary phenomena. The universe's most permanent-seeming objects were actually mortal, doomed to fade away into the expanding darkness, like dying stars. In the far future, when all the stars had burned out and all the galaxies had drifted apart, the cosmos would be populated not by matter, but by a thin soup of elementary particles growing ever colder as space itself expanded toward a final state of perfect entropy. The implications cascaded through every branch of theoretical physics, like a stone thrown into still water. If Hawking was correct, then the ultimate fate of the universe was not the heat death that physicists had long predicted, but something far stranger, a cosmos populated only by radiation, where the very concept of matter had become obsolete. But buried within this revolutionary discovery lay a paradox that would haunt theoretical physics for decades to come. A contradiction so fundamental that it threatened to tear apart the very foundations of scientific understanding. According to the sacred principles of quantum mechanics, information, the precise arrangement of particles and their properties, the detailed specification of any physical system, could never be truly destroyed. It might be scrambled beyond recognition, hidden in correlations too complex to decode, or transformed into forms that defied human comprehension. But it could never simply vanish from existence. This principle, known as unitarity, was as fundamental to physics as the conservation of energy itself. Every interaction between particles, every transformation of matter, every process in the universe had to preserve the total amount of information, even if that information became impossible to extract in practice. Yet Hawking radiation appeared to violate this most sacred law. As a black hole evaporated, the thermal radiation it emitted seemed to carry no memory whatsoever of what had fallen into it. Every book that had crossed the event horizon, every arrangement of atoms that had been consumed, every trace of the complex information structures that had once existed, all of it appeared to be erased forever when the black hole finally disappeared in its last explosive gasp. The paradox cut like a blade through the heart of physical law itself. If information could be destroyed in black holes, then quantum mechanics, one of the most successful theories in the history of science, a framework that had explained everything from the structure of atoms to the behavior of semiconductors, was fundamentally flawed. The equations that described the interactions of particles, the quantum fields that gave rise to all forces and matter, the very mathematical language in which the universe seemed to speak, all of it would be built on foundations of sand. Hawking himself seemed to embrace this radical conclusion with characteristic intellectual courage. In scientific conferences and research papers, he argued that information was indeed destroyed when black holes evaporated, and that physicists would have to abandon their cherished principle of information conservation. The black hole information paradox, as it became known, represented nothing less than a crisis at the very core of theoretical physics. For 20 years, the paradox remained unsolved, a gaping wound in the heart of scientific understanding that refused to heal. Brilliant minds proposed various solutions. Perhaps the information leaked out slowly as the black hole evaporated, encoded in subtle quantum correlations in the Hawking radiation that would require impossible precision to decode. Perhaps black holes never evaporated completely, leaving behind microscopic remnants that preserved the information forever, like cosmic libraries written in a language beyond human comprehension. But in 1995, a theoretical physicist at Stanford University named Leonard Susskind proposed a solution so radical, so completely counter to human intuition, that it would not merely resolve the paradox, but revolutionize humanity's understanding of the very nature of reality itself. In 1995, 20 years after Hawking's revolutionary discovery had torn open a wound in the heart of physics, Leonard Susskind sat in his office at Stanford University, contemplating what many considered an impossible problem. The black hole information paradox had resisted every attempt at resolution, standing like an impenetrable wall between quantum mechanics and general relativity. But Susskind, a theoretical physicist known for his unconventional thinking and willingness to challenge established wisdom, was about to propose a solution so audacious that it would fundamentally alter humanity's perception of reality itself. The insight came not from complex calculations or sophisticated computer models, but from a simple yet profound question. What if information never actually falls into a black hole at all? What if the very premise that had created the paradox was wrong? Susskind began to envision a scenario that defied every intuitive notion about space, time, and the nature of physical reality. According to his radical proposal, anything approaching a black hole would indeed appear to fall through the event horizon when viewed from its own reference frame. But from the perspective of an outside observer, something completely different would occur. As the falling object approached the event horizon, time dilation would slow its descent to a crawl. The object would appear to freeze at the boundary, its image redshifted and stretched until it became a thin. More importantly, all the information contained within that object, every atom's position, every quantum state, every detail of its structure, would become encoded on the black hole's surface like data written on a cosmic hard drive. The three-dimensional object would be transformed into a two-dimensional holographic representation, preserving every bit of information while appearing to exist in a completely different form. This concept, which Susskind termed the holographic principle, suggested something far more revolutionary than a mere solution to Hawking's paradox. If the three-dimensional interior of a black hole could be completely described by information encoded on its two-dimensional surface, then perhaps this principle extended far beyond black holes themselves. Perhaps the entire universe operated according to this same holographic logic. The mathematical framework supporting this seemingly impossible idea emerged from the cutting edge of theoretical physics. String theory, the ambitious attempt to unify quantum mechanics and gravity by describing all fundamental particles as tiny vibrating strings, had been struggling with its own set of paradoxes and inconsistencies. But in the context of the holographic principle, string theory began to reveal new possibilities that had previously been hidden. The breakthrough came in 1997, when a young physicist named Juan Maldacena at the Institute for Advanced Study in Princeton made a discovery that would shake the foundations of theoretical physics. Working with the mathematical structures of string theory, Maldacena found a precise correspondence between gravity operating in a higher dimensional space and quantum field theory existing on that space's lower dimensional boundary. This AD-CFT correspondence, as it became known, was not merely an analogy or approximation. It was an exact mathematical equivalence. Everything happening in a five-dimensional anti-de Sitter space, including the full complexity of gravitational interactions, could be perfectly described by a four-dimensional conformal field theory living on the boundary of that space. The interior gravity and the boundary quantum theory were not just similar, they were the same physics. Expressed in different mathematical languages, the implications sent shockwaves through the global physics community. If Maldacena's correspondence was correct, then the holographic principle was not just a clever solution to an isolated paradox, it was a fundamental feature of reality itself. Space, matter, energy, and even time might emerge from information processing occurring on a distant boundary surface, like a cosmic hologram of unimaginable sophistication. The philosophical implications were staggering. Every human being, every star, every galaxy, all of it might be nothing more than interference patterns in a holographic projection, shadows cast by information encoded on a boundary so remote that it lay beyond the reach of light itself. The depth that humans perceived, the three-dimensional volume of space between atoms, the vast distances that separated Earth from the stars, all of it could be an elaborate illusion, no more real than the three-dimensional images that emerged from the flat surface of a holographic plate. Yet this illusion would be perfect, complete in every detail. The holographic universe would contain all the complexity, all the beauty, all the meaning that humanity had ever discovered or ever could discover. Love would still feel real, beauty would still inspire wonder, and consciousness would still contemplate its own existence. But all of it would emerge from patterns of information dancing on an inconceivably distant surface. The mathematical evidence continued to accumulate as physicists explored the implications of holographic theories. Computer simulations showed that the holographic principle could explain puzzling features of black hole physics that had resisted conventional explanation. The entropy of a black hole, a measure of the information it contained, was proportional to the area of its event horizon, not its volume, exactly as the holographic principle predicted. Even more compelling was the realization that this relationship extended far beyond black holes. The maximum amount of information that could be stored in any region of space was limited not by its volume, but by the area of its boundary surface. This fundamental limit, known as the Bekenstein bound after physicist Jacob Bekenstein, who first derived it, suggested that reality itself was inherently two-dimensional, with the appearance of three-dimensional space emerging as a secondary phenomenon. The holographic principle also offered new insights into the nature of quantum entanglement, the mysterious connection between particles that Einstein had famously dismissed as spooky action at a distance. In a holographic universe, entanglement might be the mechanism by which space itself was woven together. Strongly entangled regions would appear close in space, while weakly entangled regions would seem far apart. The fabric of space-time would be literally constructed from these ghostly quantum connections. This insight led to even more profound realizations about the nature of reality. If space emerged from quantum entanglement, then the expansion of the universe might reflect changes in the pattern of entanglement across the cosmic boundary. Dark energy, the mysterious force accelerating cosmic expansion, could be understood as the signature of decreasing entanglement, causing space to stretch and grow as the connections between distant regions weakened over cosmic time. The evidence was not merely theoretical. Observations of the cosmic microwave background radiation showed correlations over distances so vast that light could never have traveled between them in the time since the Big Bang. These correlations could be explained by cosmic inflation, a period of rapid expansion in the universe's earliest moments. But they could equally well be signatures of a holographic reality where information from widely separated regions was encoded on the same boundary surface. Even the fine-tuning of fundamental constants that allowed for the existence of stars, planets, and life itself took on new meaning in a holographic context. Rather than requiring an infinite multiverse to explain why the laws of physics seemed perfectly calibrated for complexity and consciousness, the holographic principle suggested that these constants might emerge naturally from the information processing occurring at the cosmic boundary. As physicists delved deeper into the mathematics of holographic reality, they discovered that the principle extended beyond cosmology into the realm of consciousness itself. If the brain processed information holographically, with each region containing information about the whole, then perhaps consciousness was not localized to specific neural networks, but distributed across the entire structure of thought and memory. The implications cascaded through every domain of human knowledge, From neuroscience to philosophy to the deepest questions about the meaning of existence. If reality was holographic, then the boundary between observer and observed, between mind and matter, between inside and outside, might be nothing more than a convenient fiction, a way of organizing experience that had no fundamental basis in the structure of the universe itself. Standing at the threshold of this revelation, humanity found itself confronting not just a new theory of physics, but a complete reconceptualization of what it meant to exist in a universe that might be far stranger and more beautiful than anyone had ever dared to imagine. As the holographic principle gained acceptance among theoretical physicists, a new generation of researchers began to search for evidence that our own universe might indeed be a vast hologram projected from information encoded on its most distant boundary. The quest would require the most sensitive instruments ever devised, capable of detecting the subtle signatures of a reality that existed not in 3 dimensions, but as patterns of information dancing on a cosmic surface. The first hints came from an unexpected source: the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space like the fading echo of creation itself. This ancient light, released when the universe first became transparent, some 380,000 years after its birth, carried within its subtle fluctuations a record of the universe's earliest moments, and potentially the signatures of its holographic nature. When the Planck satellite, Europe's most advanced cosmic microwave background observatory, began its observations in 2009, it revealed temperature variations in this primordial radiation with unprecedented precision. These tiny fluctuations, differing by mere millionths of a degree, represented the seeds from which all cosmic structure would eventually grow, the quantum uncertainty that would blossom into galaxies, stars, and worlds. But buried within this cosmic baby picture were correlations that defied conventional explanation. Temperature fluctuations in regions of sky separated by vast distances showed mysterious connections, as if information from one part of the early universe had somehow influenced conditions in regions that should have been completely isolated from each other. These correlations extended far beyond what could be explained by the speed of light, suggesting that the early universe had achieved a level of coordination that seemed to violate the fundamental limits of causality. The standard explanation for these correlations was cosmic inflation, a period of exponential expansion in the universe's first fraction of a second that stretched quantum fluctuations to cosmic scales. But the holographic principle offered an alternative interpretation. If the universe was indeed a hologram, then regions that appeared to be widely separated in 3-dimensional space might actually be adjacent when viewed from the perspective of the 2-dimensional boundary, where all information was ultimately encoded. The evidence continued to accumulate as astronomers made increasingly precise measurements of cosmic structure. The distribution of galaxies across the universe showed patterns that could be explained by holographic information processing, with large-scale correlations emerging naturally from the way information was organized on the cosmic boundary. Dark matter, the invisible substance that comprised most of the universe's mass, exhibited gravitational effects that matched the predictions of holographic models with startling accuracy. In 2013, a team led by Yoshifumi Hyakutake at Ibaraki University in Japan provided the first direct computational evidence supporting the holographic principle. Using sophisticated computer simulations, Hyakutake's group calculated the internal energy of a black hole using 2 completely different approaches. One, treating it as a conventional 3-dimensional object described by Einstein's general relativity. and another using the holographic description, where all information existed on the two-dimensional event horizon surface. The results were identical to within computational precision. The first concrete proof that the mathematics of holographic reality actually worked in practice. The three-dimensional interior and the two-dimensional boundary were not merely analogous, but mathematically equivalent, containing exactly the same information expressed in different forms. What appeared to be a solid, three-dimensional object with complex internal structure was perfectly equivalent to patterns of information encoded on a distant surface. The implications of Hyakutake's calculation rippled through the physics community like a stone thrown into still water. If black holes were indeed holographic, then the principle might extend to every region of space-time, including the observable universe itself. Humanity might be living inside a cosmic hologram of almost incomprehensible sophistication, where every atom, every force, every moment of experience emerged from information processing occurring on a boundary so distant it lay beyond the reach of the most powerful telescopes. Further evidence came from studies of quantum entanglement, the strange connection between particles that maintain their mysterious correlation regardless of the distance separating them. Researchers found that the pattern of entanglement in quantum systems matched exactly what would be expected if space itself emerged from these ghostly connections. Regions with strong entanglement appeared close together in space, while weakly entangled regions seemed far apart, as if the fabric of reality was literally woven from quantum correlations. This insight led to a profound realization about the nature of space-time itself. Rather than being a fixed stage upon which matter and energy played out their cosmic drama, space might be an emergent phenomenon arising from the complex dance of quantum information. When entanglement was strong, space contracted. When it weakened, space expanded, potentially explaining the accelerating expansion of the universe as a consequence of decreasing quantum correlations across cosmic time. The discovery of gravitational waves by the LIGO and Virgo collaborations provided another window into the holographic nature of reality. These ripples in space-time, created by the collision of black holes and neutron stars, carried information about the most extreme environments in the universe. But in a holographic reality, gravitational waves would not be disturbances propagating through three-dimensional space. They would be changes in the information structure encoded on the cosmic boundary, manifesting as apparent motion in the emergent holographic projection. Careful analysis of gravitational wave signals revealed subtle patterns that matched the predictions of holographic models. The way these waves propagated through space, the manner in which they encoded information about their sources, and their interaction with matter all showed signatures consistent with a universe where three-dimensional reality emerged from two-dimensional information processing. Even more intriguing were observations of the cosmic web, the vast network of filaments and voids that organized matter on the largest scales. This cosmic architecture showed patterns reminiscent of neural networks, with dense nodes connected by elongated filaments spanning billions of light years. In a holographic universe, these structures might represent the physical manifestation of information processing networks encoded on the cosmic boundary, the universe's way of computing its own existence. The evidence extended beyond cosmology into the realm of particle physics itself. Experiments at the Large Hadron Collider revealed new insights into the fundamental nature of matter and energy, showing that particles behaved in ways consistent with holographic theories. The vacuum of space, rather than being empty, appeared to be filled with quantum fields that might represent the computational substrate of holographic reality. Perhaps most remarkably, studies of consciousness and information processing in biological systems revealed holographic principles at work throughout the natural world. The human brain appeared to store and process information holographically, with memories distributed across neural networks rather than localized in specific regions. Each part of the brain contained information about the whole, just as each region of a hologram contained information about the entire image. This suggested that consciousness itself might be holographic in nature, arising not from specific neural computations, but from the emergent properties of information processing distributed across complex networks. If the universe was indeed a hologram, then consciousness might be the universe's way of experiencing itself from within its own projection. The cosmos achieving self-awareness through the emergence of minds capable of contemplating their own existence. As evidence for the holographic nature of reality continued to accumulate, humanity found itself standing at the threshold of a revelation that would transform not just physics and cosmology, but the very meaning of existence itself. The universe that had seemed so solid, so three-dimensional, so fundamentally real, might be nothing more than the most sophisticated illusion ever conceived, a holographic projection of infinite beauty and complexity arising from information encoded on the edge of everything. As the evidence for a holographic universe mounted, physicists began to contemplate implications that stretched the boundaries of scientific imagination beyond all recognition. If humanity was indeed living inside a cosmic hologram, then the nature of this holographic reality suggested something far more profound and unsettling than a mere alternative description of known physics. The deeper researchers probed into the mathematical structure of holographic theories, the more they realized that we might not be living in just any holographic universe. We might be living inside a black hole of cosmic proportions. The possibility had been lurking in the equations for years, hidden within the mathematical correspondence between black hole interiors and holographic boundaries. If the holographic principle applied to our universe, then there must exist some distant surface upon which all the information describing our reality was encoded. But where was this boundary, and what lay beyond it? Theoretical physicist Raúl Carballo Rubio at the University of Granada had been wrestling with these questions when he made a connection that would send shockwaves through the cosmology community. In 2014, his calculations suggested that our Big Bang might not have been the beginning of everything, but rather the birth of a white hole, the theoretical time-reversed opposite of a black hole, where matter and energy explode outward rather than collapsing inward. According to Carballo Rubio's model, if a black hole from a previous universe had collapsed completely past its own internal horizon, the extreme curvature of space-time might have caused it to rebound catastrophically, creating a white hole that would appear to external observers as a cosmic explosion, a Big Bang. We would be living inside the expanding interior of what had once been a black hole in another reality, experiencing the ongoing expansion of space as the white hole continued to grow. This model explains several cosmic mysteries that had long puzzled astronomers. The uniform temperature of the cosmic microwave background radiation, which showed the same temperature in all directions to within parts per million, had always been difficult to explain. How could regions of the early universe that had never been in causal contact achieve such perfect thermal equilibrium? In a black hole interior model, these regions would have been in contact before the original black hole's formation, naturally explaining their shared temperature. The flatness of space, the observation that the geometry of the universe appeared to be perfectly balanced between eternal expansion and eventual collapse, also found a natural explanation. The interior of a black hole would have precisely the critical density needed to maintain this delicate balance, neither expanding so rapidly that matter could never clump together, nor collapsing so quickly that structures had no time to form. Even more remarkably, the model predicted that our universe should be accelerating its expansion, driven by the same dark energy that astronomers had discovered in 1998. This acceleration would be the signature of the universe approaching the black hole's inner horizon, where space-time curvature becomes so extreme that space itself begins to stretch exponentially. But the implications went far deeper than explaining observable phenomena. If we were living inside a black hole, then our entire cosmic history, from the Big Bang to the present moment, might be playing out in what appeared to external observers as an infinitely brief instant. Time dilation at the event horizon meant that while billions of years passed within the black hole, only moments would pass in the external universe. This realization cast human existence in a dramatically different light. Every moment of history, every life ever lived, every thought ever contemplated, might be compressed into a single quantum fluctuation from the perspective of the parent universe. Yet, within that fluctuation, entire civilizations could rise and fall. Consciousness could emerge and contemplate its own existence, and the full richness of experience could unfold across cosmic time. The boundary of our holographic universe, the surface upon which all information about our reality was encoded, would be the event horizon of this cosmic black hole. This horizon would lie beyond our observable universe, constantly receding as space expanded, but always present as the ultimate boundary of everything we could ever know or experience. We were prisoners of the most perfect prison ever conceived, unable to even perceive the walls of our cosmic cell. Some models suggested even more unsettling possibilities. If dark energy continued to accelerate cosmic expansion, we might eventually approach the black hole's inner horizon, where space-time curvature becomes infinite and the very concept of space and time breaks down. This cosmic singularity would represent the end of everything, not just matter and energy, but space and time themselves would cease to exist in any meaningful sense. The approach to this final boundary might already be beginning. The acceleration of cosmic expansion, which appeared to be increasing over time, could be the first sign that our holographic universe was approaching its ultimate limits. As we drew closer to the inner horizon, space would stretch more rapidly, matter would become increasingly diluted, and the universe would enter a phase of exponential expansion that would tear apart every structure from galaxies to atoms themselves. Yet even this cosmic apocalypse might be an illusion. From the perspective of the holographic boundary, all information about our universe's history, past, present, and future, would be encoded simultaneously on the event horizon surface. Our experience of time's passage, of cause and effect, of birth and death, might be nothing more than the subjective experience of information being processed on this distant boundary. The possibility raised profound questions about the nature of multiple universes. If our cosmos was the interior of a black hole in another universe, then what prevented that parent universe from also being a holographic projection? The mathematics suggested an infinite regression of universes within universes, each one encoded holographically on the boundary of a black hole. In the next level of reality, black holes within our own universe might themselves contain entire cosmos, complete with their own galaxies, stars, and perhaps even conscious beings contemplating their own existence. Every time matter crossed an event horizon in our universe, it might be giving birth to a new reality, seeded with the information patterns that would determine its physical laws, its cosmic structure, and its potential for complexity and life. This fractal cosmology suggested that consciousness might be far more prevalent in the universe than previously imagined. Rather than being rare accidents emerging from specific arrangements of matter, conscious beings might exist at every level of the cosmic hierarchy, each convinced that their holographic reality was the fundamental layer of existence. The implications for human understanding were staggering. If we were living inside a black hole, then escape was not merely difficult, it was literally impossible. The event horizon that defined our cosmic boundary was also an absolute barrier beyond which no information could ever pass. We were forever cut off from the parent universe that had given us birth, unable to send signals or even evidence of our existence to the reality beyond. Yet perhaps escape was not the goal. If our holographic universe contained all the complexity, beauty, and meaning that consciousness could ever discover, then the question of what lay beyond our cosmic boundaries might be irrelevant. We were not diminished by existing as patterns of information on a distant surface. We were the universe's way of experiencing itself, consciousness emerging from the cosmic hologram to contemplate the mystery of its own existence. The holographic principle opened doorways to theories that stretched the very limits of scientific imagination, revealing possibilities that challenged every assumption about the nature of reality, consciousness, and existence itself. As physicists explored the mathematical landscape of holographic universes, they discovered that our cosmos might be just one projection among countless others, each emerging from information encoded on its own boundary surface in a vast multiverse of unimaginable scope and complexity. The mathematical foundation for this cosmic hierarchy emerged from string theory, the ambitious attempt to describe all fundamental particles and forces as vibrations of tiny, one-dimensional strings existing in higher dimensional spaces. In the context of the holographic principle, string theory revealed that reality might be organized as an infinite nested structure, with each level of existence encoded holographically on the boundary of the next. According to these models, the two-dimensional surface that encoded our three-dimensional universe was itself embedded in a higher dimensional space, which might in turn be a holographic projection of information encoded on an even more distant boundary. This created an infinite tower of realities, each one believing itself to be fundamental, while actually being a shadow cast by information processing occurring at deeper levels of existence. The implications were staggering. Every black hole in our universe might be a portal to another holographic reality, complete with its own physical laws, its own cosmic history, and its own potential for complexity and consciousness. The supermassive black hole at the center of our galaxy, Sagittarius A star, might contain a universe with billions of galaxies, each hosting countless stars and planets, where conscious beings contemplated their own existence, never suspecting that their entire cosmos was encoded on the event horizon of a black hole in another reality. Information theory, the mathematical framework that describes how information is processed, stored, and transmitted, provided crucial insights into the structure of this holographic multiverse. Jacob Bekenstein's discovery that the maximum information content of any region was proportional to its surface area rather than its volume suggested that reality itself was fundamentally two-dimensional, with higher dimensions emerging as projections from this underlying information substrate. This insight led to a profound realization about the nature of physical law itself. Rather than being fixed properties of space-time, the constants that determined the strength of fundamental forces, the masses of particles, and the structure of atoms might emerge from the way information was organized and processed on the holographic boundary. Different patterns of information encoding could give rise to universes with completely different physics, where gravity might be stronger or weaker, where atoms might be impossible to form, or where entirely new forms of matter and energy could exist. The holographic principle also shed new light on the mystery of dark matter and dark energy, the invisible components that comprised 95% of our universe's mass and energy. Rather than being exotic particles or fields existing in our three-dimensional space, these phenomena might be shadows cast by information processing occurring on the cosmic boundary. Dark matter's gravitational effects would emerge from the way matter information was encoded on the holographic surface, while dark energy's accelerating expansion might reflect changes in the information structure itself. Quantum entanglement, the mysterious connection between particles that had puzzled physicists since the early days of quantum mechanics, took on new meaning in holographic theories. Einstein had dismissed entanglement as spooky action at a distance, but in a holographic universe, these connections might be the very mechanism by which space itself was constructed. Strongly entangled regions would appear close together in the emergent three-dimensional projection, while weakly entangled regions would seem far apart. This insight suggested that the fabric of space-time was literally woven from quantum entanglement, with the geometry of space emerging from the pattern of correlations between information encoded on the boundary. When entanglement was strong, space would contract. When it weakened, space would expand. The accelerating expansion of our universe might therefore reflect a cosmic decrease in entanglement. As quantum correlations across the boundary surface gradually weakened over time. The holographic principle also offered new perspectives on the nature of time itself. In conventional physics, time was treated as a dimension analogous to space, flowing from past to future in a uniform stream. But in holographic theories, time might emerge from the sequential processing of information on the boundary surface. The universe's history, past, present, and future, would be encoded simultaneously on the holographic boundary, with the subjective experience of temporal flow arising from the way conscious beings processed this timeless information. This suggested that the past was not fixed and the future not open, but rather that all moments of cosmic history existed simultaneously as static information patterns on the boundary surface. What humans experienced as the passage of time might be nothing more than the subjective experience of reading this cosmic database, with consciousness serving as the universe's way of experiencing its own information content, sequentially rather than all at once. Perhaps most remarkably, the holographic principle suggested that consciousness itself might be a fundamental feature of reality, rather than an emergent accident. If the universe was information, and if information processing was required to maintain the holographic projection, then consciousness might be the mechanism by which the cosmos sustained its own existence. Every conscious being would be a node in a vast information processing network, contributing to the computational substrate that maintained the holographic reality. This led to speculation that consciousness might be far more prevalent in the universe than previously imagined, rather than being rare accidents emerging from specific arrangements of matter. Conscious beings might exist at every level of the cosmic hierarchy, each contributing to the information processing that sustained their level of reality. The apparent fine-tuning of physical constants that allowed for the emergence of complexity and life might not be a cosmic coincidence, but a necessity. Consciousness might be required for the universe to exist at all. Some theories went even further, suggesting that individual conscious beings might have the power to influence the holographic projection through their observations and intentions. If reality emerged from information processing, and if consciousness played a role in that processing, then the act of observation might literally help create the universe being observed. This would transform the relationship between mind and matter from one of passive observation to active participation in the creation of reality itself. The multiverse of holographic realities might be infinite, not just in extent, but in diversity. Different boundary surfaces could encode universes with completely different dimensionalities, where space might have 2 dimensions instead of 3, or where time might flow in multiple directions simultaneously. Some holographic universes might contain only energy and no matter, while others might be composed entirely of information with no material substrate at all. Yet despite this infinite diversity, all holographic realities would share certain fundamental features. They would all emerge from information encoded on boundary surfaces. They would all be subject to the limitations imposed by the holographic principle, and they would all contain within themselves the potential for further layers of holographic projection. The multiverse would be a fractal structure of infinite depth and complexity, with consciousness emerging at every level to contemplate the mystery of its own existence. As physicists continued to explore these possibilities, they realized that the holographic principle represented not just a new theory of physics, but a complete reconceptualization of what it meant to exist in a universe that might be far stranger and more beautiful than anything humanity had ever imagined. The quest to detect evidence of our universe's holographic nature has driven physicists to develop the most sensitive instruments ever conceived, machines capable of measuring fluctuations in space-time itself and searching for the subtle signatures of a reality that exists as information encoded on a distant boundary. These experiments represent humanity's most ambitious attempt to peer beyond the veil of 3-dimensional experience and glimpse the fundamental information substrate from which all existence might emerge. At Fermilab, America's premier particle physics laboratory, a remarkable machine called the holometer began operations in 2014 with a mission that seemed torn from science fiction: to measure whether space itself is quantized into discrete units, pixelated like a cosmic hologram at the smallest possible scales. The device operates on principles borrowed from the most precise measurements in physics, using laser interferometry to detect fluctuations in spacetime that would be unimaginably tiny, smaller than the nucleus of an atom compared to the distance between Earth and the Sun. The holometer consists of 2 powerful lasers whose beams are split and sent down perpendicular arms, extending 40 meters in each direction. If space is smooth and continuous, as assumed by classical physics, these laser beams should maintain perfect interference patterns when recombined. But if space has a fundamental granularity, if reality is pixelated at the Planck scale, the smallest meaningful unit of distance in physics, then tiny fluctuations in the interference patterns would reveal what researchers call holographic noise. This noise would be the signature of information processing occurring at the universe's most fundamental level, the quantum foam, where virtual particles pop in and out of existence and space-time itself becomes uncertain. In a holographic universe, this quantum foam would represent the computational substrate where the information encoding our three-dimensional reality is processed and projected. The holometer's exquisitely sensitive measurements probe deep into this realm, searching for evidence that our seemingly solid reality emerges from discrete information bits. Initial results from the holometer showed no holographic noise at the level predicted by some theoretical models. But this negative result was itself scientifically valuable. It ruled out certain versions of holographic theories, while pointing researchers toward more sophisticated models that might encode information in ways too subtle for current technology to detect. The absence of obvious pixelation at the Planck scale suggested that if the universe is indeed holographic, the mechanism is far more elegant and complex than simple digital encoding. Meanwhile, the Event Horizon Telescope, a global network of radio telescopes working in perfect coordination, has provided humanity's first direct observations of black hole event horizons, the very boundaries where the holographic principle should be most clearly manifested. In 2019, this remarkable instrument captured the first image of the supermassive black hole M87 star, revealing a dark shadow surrounded by a brilliant ring of superheated matter spiraling toward its doom. Almost. But for holographic physicists, the most important features of this image were not what could be seen, but what could be inferred about information storage at the event horizon. The shadow's precise size and shape matched theoretical predictions for how information would appear to be encoded on the black hole's surface when viewed from the outside. Matter approaching the event horizon appeared to slow down and spread out, exactly as holographic theories predicted, with all its information content becoming encoded on the two-dimensional boundary rather than disappearing into the three-dimensional interior. Subsequent observations of the black hole at the center of our own galaxy, Sagittarius A, provided additional confirmation of holographic behavior. The way matter behaved near these cosmic monsters, stretching, slowing, and appearing to freeze at the event horizon, matched the predictions of holographic models with remarkable precision. Information was indeed being preserved on the boundary surface, suggesting that the holographic principle operated not just in theoretical calculations, but in the actual physics of real black holes. Gravitational wave detectors like LIGO and Virgo have opened another window into the holographic nature of reality. These instruments, sensitive enough to measure distortions in space-time smaller than 1/10,000th the width of a proton, detect ripples created by the most violent events in the universe, colliding black holes and neutron stars. But in a holographic universe, gravitational waves would not be disturbances propagating through three-dimensional space. They would be changes in the information structure encoded on the cosmic boundary. Careful analysis of gravitational wave signals has revealed subtle patterns consistent with holographic models. The way these waves propagate through space, their polarization properties, and their interaction with matter all show signatures that match theoretical predictions for a universe where space-time emerges from information processing. Each gravitational wave detection provides new data about the fundamental structure of reality, gradually building a picture of a cosmos that might indeed be holographic in nature. The James Webb Space Telescope, humanity's most powerful observatory, has joined the search for holographic signatures by peering deeper into the universe's past than ever before. Its infrared vision penetrates cosmic dust to observe the first galaxies that formed after the Big Bang, searching for anomalies in their structure and distribution that might reveal the holographic nature of space itself. Early observations have revealed patterns in the cosmic web, the vast network of filaments and voids that organize matter on the largest scales, that show remarkable similarities to information processing networks. These structures appear to evolve over cosmic time in ways consistent with holographic models, with matter organizing itself according to patterns that might reflect the underlying information architecture encoded on the cosmic boundary. Particle accelerators like the Large Hadron Collider provide another probe of holographic physics by recreating the extreme conditions that existed in the universe's earliest moments. When protons collide at near light speed, they create brief fireballs of quark-gluon plasma, a state of matter that existed microseconds after the Big Bang. The behavior of this plasma shows properties consistent with holographic theories, flowing like a nearly perfect fluid in ways that match theoretical predictions for how information would behave when encoded holographically. Perhaps most intriguingly, quantum computing experiments have begun to explore the information-theoretic foundations of reality itself. By manipulating quantum states with unprecedented precision, researchers can simulate simplified versions of holographic systems and study how information propagates and processes in quantum networks. These experiments suggest that the computational power required to sustain a holographic universe might be achievable through quantum information processing, with consciousness potentially playing a role in the cosmic computation. Neuroscience has also contributed to the search for holographic principles in nature. Studies of brain function reveal that memory and consciousness appear to operate holographically, with information distributed across neural networks rather than stored in specific locations. Each region of the brain contains information about the whole, just as each part of a hologram contains information about the entire image. If consciousness is indeed holographic, this might reflect the deeper holographic structure of reality itself. Astronomical surveys using advanced telescopes and supercomputing networks continue to map the universe's large-scale structure with increasing precision, searching for subtle correlations and patterns that might reveal holographic encoding. The distribution of dark matter, the cosmic microwave background radiation, and the formation of the first stars all provide potential signatures of a universe where three-dimensional structure emerges from two-dimensional information. As these diverse experimental programs continue to generate data, physicists are building an increasingly detailed picture of a cosmos that might indeed be holographic in nature. While definitive proof remains elusive, the accumulating evidence suggests that humanity may be living inside the most sophisticated information processing system ever conceived, a universe that exists as patterns of data encoded on the edge of everything we can ever know or experience. The convergence of evidence from multiple independent sources, gravitational waves, black hole observations, cosmic microwave background studies, and quantum experiments points toward a reality far stranger than classical physics ever imagined. Each new measurement brings scientists closer to answering the ultimate question: are we truly living inside a cosmic hologram? Or do these phenomena have more conventional explanations that preserve our intuitive understanding of three-dimensional space? The stakes of this investigation extend far beyond academic physics. If the holographic principle is correct, it would represent the most profound revolution in human understanding since Copernicus displaced Earth from the center of the cosmos. We would be forced to confront the possibility that everything we experience as solid, three-dimensional reality, is actually information encoded on an inconceivably distant boundary, a cosmic hologram of infinite beauty and complexity. Yet, even as technology advances and experiments become more sophisticated, the deepest questions about holographic reality may ultimately transcend what can be measured by any instrument. The search for proof of our universe's holographic nature is simultaneously a search for understanding of consciousness, meaning, and the fundamental nature of existence itself. Whether we live in 3 dimensions or 2, whether space is real or emergent, whether time flows or is simply processed, these questions probe the very heart of what it means to be conscious beings, contemplating the mystery of our own existence. As humanity stands at the threshold of potentially discovering that reality itself is a holographic projection, the implications ripple through every domain of human experience, like waves spreading across the still surface of a cosmic pond. If we are indeed living inside a holographic black hole, encoded as information on a boundary so distant it lies beyond the reach of light itself, then the fundamental questions that have haunted consciousness since the dawn of self-awareness take on meaning so profound they challenge the very foundations of what it means to exist. The revelation transforms the nature of identity itself. In a holographic universe, the boundaries between self and cosmos, between observer and observed, between mind and matter, dissolve into something far more mysterious and interconnected. Each conscious being becomes not merely a collection of atoms arranged by cosmic accident, but a unique expression of the universe experiencing itself subjectively, a localized pattern of information processing within the vast computational substrate that maintains the holographic projection. This perspective suggests that individuality, while experientially real, might be fundamentally illusory. If all information about the universe is encoded on every part of the boundary surface, then each person contains, in some profound sense, the entire cosmos within their being. We are not separate entities moving through an external universe. We are the universe itself, achieving self-awareness through countless individual perspectives. Each one, a unique window through which the cosmic hologram contemplates its own existence. The holographic principle reframes the ancient philosophical question of whether consciousness creates reality or reality creates consciousness. In a universe where space, time, and matter emerge from information processing, consciousness might not be an accidental byproduct of material complexity, but a fundamental requirement for existence itself. The universe might literally need conscious observers to process the information that maintains its holographic projection, making awareness not a rare cosmic accident, but an essential feature of reality. This insight casts human existence in a dramatically different light. Rather than being insignificant specks of matter clinging to a tiny rock orbiting an ordinary star in an unremarkable galaxy, conscious beings become active participants in the creation and maintenance of reality itself. Every thought, every observation, every moment of awareness contributes to the vast information processing network that sustains the holographic universe. We are not merely in the cosmos. We are the cosmos, experiencing itself from within its own projection. Time, in a holographic universe, loses its conventional meaning as a flowing river carrying events from past to future. Instead, it becomes something more akin to a dimension of information, with all moments of cosmic history existing simultaneously as static patterns encoded on the boundary surface. What humans experience as temporal flow might be the subjective experience of consciousness reading this cosmic database, processing the timeless information that describes the universe's entire history. This temporal holography suggests that the past is not fixed in the way we imagine. nor is the future entirely open. All possibilities, all choices, all moments of existence are encoded simultaneously on the boundary, with consciousness serving as the mechanism by which specific sequences of information are experienced as coherent narratives of cause and effect. Free will, rather than being an illusion, might be the universe's way of exploring its own information content, with each conscious choice representing a path through the vast space of encoded possibilities. Death, in such a reality, takes on meanings that transcend the conventional understanding of endings and beginnings. If consciousness is information, and if information is conserved on the holographic boundary, then some pattern of individual existence might persist long after physical forms have dissolved back into the cosmic substrate. We become part of the eternal information structure that defines reality itself, our lives encoded forever in the holographic memory of the universe. Yet this potential immortality comes with a profound twist. If our entire cosmic history, from the Big Bang to the heat death of the universe, is playing out in what appears to external observers as an infinitely brief instant, then all human experience, all suffering and joy, all love and loss, might be compressed into a single quantum fluctuation from the perspective of the parent reality. This raises unsettling questions about the nature of meaning in a holographic existence. But perhaps meaning is not diminished by being encoded in information patterns. The holographic principle suggests that complexity, beauty, and consciousness can emerge from pure information just as readily as from material substrates. A symphony is not less beautiful for being encoded as patterns of magnetic fields on a hard drive. Love is not less real for arising from neural information processing. The cosmos is not less magnificent for potentially being a holographic projection. The implications extend to humanity's relationship with the broader universe. If black holes within our cosmos contain their own holographic realities, complete with galaxies, stars, and perhaps conscious beings, then we become part of an infinite hierarchy of existence. Every time matter crosses an event horizon in our universe, it might seed a new reality with its own potential for complexity, consciousness, and meaning. We are not merely products of cosmic evolution, but active participants in cosmic reproduction, helping to create new universes through the very process of existence. This fractal cosmology suggests that consciousness might be far more prevalent than previously imagined. Rather than being rare accidents emerging from specific arrangements of matter, aware beings might exist at every level of the cosmic hierarchy, each convinced that their holographic reality represents the fundamental layer of existence. The universe becomes not a largely empty void punctuated by isolated islands of awareness, but a vast ocean of consciousness exploring itself through infinite perspectives. The search for meaning in a holographic universe ultimately returns to the mystery of consciousness itself. Whether we exist as patterns of matter in three-dimensional space or as information encoded on a two-dimensional boundary might be less important than the fact that we exist at all, that the universe has achieved the miracle of self-awareness, regardless of the mechanism by which this awareness arises. Perhaps the deepest truth revealed by the holographic principle is that the universe is not a collection of objects existing in space and time, but a unified information structure experiencing itself subjectively through countless individual perspectives. We are not separate from the cosmos, but expressions of it, not observers of reality, but reality itself achieving consciousness. In this light, the question of whether we are living inside a black hole becomes secondary to the more profound realization that we are living, conscious, and capable of contemplating these ultimate mysteries. Whether our existence spans billions of years or is compressed into a quantum instant, whether we inhabit 3 dimensions or are projections from 2, whether space is fundamental or emergent, none of this diminishes the extraordinary fact that consciousness has emerged to ponder its own nature. The holographic universe, if it exists, represents the ultimate synthesis of mind and matter, information and experience, individual and cosmos. We find ourselves not as alien visitors in an indifferent universe, but as the universe itself, awakening to its own infinite mystery. Consciousness emerging from the cosmic hologram to contemplate the beauty and strangeness of its own existence. Standing at the edge of this revelation, humanity faces not the dissolution of meaning, but its ultimate transformation. We are the universe dreaming of itself, patterns of information achieving awareness, consciousness exploring the infinite depths of its own holographic nature. Whether we live in 3 dimensions or 2, whether we exist for eons or instants, whether reality is solid or projected, we are here, we are aware, and we are an integral part of the greatest mystery ever conceived. The universe's ongoing attempt to understand itself through the emergence of minds capable of contemplating their own existence. In the end, the holographic principle reveals that the most profound questions about reality cannot be answered by measurement alone, but require a fundamental shift in how consciousness understands its relationship to the cosmos. We are not merely studying the universe. We are the universe studying itself, not just observing the cosmic hologram, but participating in its creation, maintenance, and exploration. The mystery of existence is not something we solve from the outside, but something we embody from within. Conscious expressions of the infinite information structure that gives rise to all possible worlds, all possible thoughts, and all possible forms of awareness, contemplating the endless depth of their own holographic nature.